Imagine taking a tiny piece of metal, only a few millimeters wide, and zooming in. You zoom in 1,000 times, then 100,000 times, then millions of times. Eventually, something incredible appears. You're looking at individual atoms. Each tiny spot you see is an actual atom. And what makes this even more amazing is that just a few decades ago, directly seeing atoms like this was considered almost impossible. So how did scientists manage to see something so unbelievably small? The biggest problem is light. Human eyes can see visible light, but visible light has wavelengths between about 380 and 750 nanometers. An atom is roughly 0.1 nanometers across. That means an atom is thousands of times smaller than the wavelength of visible light. When the wavelength of light is much larger than the object you're trying to see, the light bends around it instead of producing a clear image. So scientists needed something with a much smaller wavelength. And they found the answer in something surprising: electrons. In 1924, French physicist Louis de Broglie proposed that matter can behave like a wave. This meant that electrons, just like light, have wavelengths. And the faster an electron moves, the shorter its wavelength becomes. By accelerating electrons to extremely high speeds, scientists could give them wavelengths far smaller than visible light. This opened the door to a completely new type of microscope. In the 1930s, physicists Ernst Ruska and Max Knoll built one of the first working electron microscopes. Instead of using glass lenses like a normal microscope, the electron microscope used electromagnetic fields to control and focus the electrons. The electrons were fired toward an extremely thin sample. Some electrons passed through the sample more easily than others, creating an electronic pattern. That pattern could then be magnified to produce an image. This became known as the transmission electron microscope, or TEM. At first, the images weren't very impressive. But scientists kept adding improvements and more powerful lenses. Eventually, electron microscopes could see things that optical microscopes could never reveal: bacteria, viruses, and structures of the nanoscale. But then scientists discovered a huge problem. The electromagnetic lenses themselves were causing distortion. This problem is called spherical aberration. Basically, electrons traveling through different parts of the lens didn't focus at exactly the same point. Instead of producing a perfectly sharp image, the electrons created a blur. And the more scientists tried to magnify the image, the worse the problem became. This created a frustrating limit. Scientists could make the electrons faster. They could make better microscopes. They could add more lenses. But eventually, the blur caused by spherical aberration stopped them from seeing atoms clearly. For decades, researchers tried to find a solution. Some scientists developed completely different types of microscopes. In the 1950s, the field ion microscope produced some of the first accepted images showing individual atoms. But there was a limitation. It could only show atoms near the extremely sharp tip of a needle. Scientists still wanted a microscope that could look directly through materials and reveal their atomic structure. Then, in the 1970s, physicist Albert Crew made another major breakthrough. He developed a much brighter and more focused electron source and combined it with scanning technology. Instead of illuminating the entire sample at once, the electron beams scanned across it point by point. This produced some of the first impressive images of individual atoms using an electron microscope. But the fundamental problem remained. Spherical aberration was still limiting the resolution. For years, it seemed like there was no way around it. Then came an unusual idea. Three scientists, Harold Rose, Maximilian Hayter, and Knut Urban, believed they could correct the distortion using specially designed electromagnetic fields. their approach sounded almost crazy. Instead of trying to create a perfect lens, they intentionally distorted the electron beam using complicated arrangements of magnets. They used multipole magnets to reshape the beam and then used another set of magnets to correct that distortion. If everything was calculated perfectly, the new system could produce an effect that essentially cancelled the spherical aberration of the original lens. For years, they struggled to make it work. The equipment was extremely complicated, expensive, and difficult to stabilize. Funding was also running out. Then, in 1997, everything changed. After another failed test, the researchers switched off the system and allowed the magnets to settle. When they turned it back on, something incredible happened. The image stabilized. The horrible distortion was dramatically reduced. And suddenly, the microscope could produce incredibly sharp images of atoms. After more than 60 years of trying to overcome the problem, scientists finally had a practical solution. This technology became known as aberration correction. The improvement was enormous. Instead of seeing a blurry collection of atoms, researchers could now distinguish individual atomic columns with extraordinary precision. And this wasn't just about taking beautiful pictures. Seeing atoms allows scientists to understand why materials behave the way they do. They can study metals, semiconductors, batteries, catalysts, nanomaterials, and countless other substances at the atomic level. They can measure distances between atoms. They can identify different elements. They can see defects in crystal structures. And they can understand how tiny changes in atomic arrangement can completely change the properties of a material. Today, scientists can place a tiny sample inside an advanced electron microscope, carefully align it, accelerate electrons through it, and zoom in until the atomic structure becomes visible. What once seemed impossible is now routine. A piece of ordinary material can be transformed into an extraordinary landscape of atoms. And perhaps the most amazing part is this: we didn't discover a way to make atoms bigger. We discovered a way to build instruments precise enough to see them. From the first crude electron microscopes of the 1930s to today's incredibly advanced machines, nearly a century of persistence, mathematics, physics, and engineering turned the impossible into reality. Today, when scientists look at an image of individual atoms, they're not just looking at tiny dots. They're looking directly at the building blocks of the world around us.